Okay, off we go. Picking up where we were last time. Attendance quiz, attendance code, all of that. Distraction there. Okay, so another example. So remember, we were talking about triple integrals. Important tool, when you have some sort of a quantity that's adding up over a three-dimensional solid. And slicing it up is this geometrically challenging process, right? Geometrically challenging, artistically challenging, right? Being able to draw a picture good enough to be able to draw the conclusions that you need to draw, right? Is no joke, right? So again, don't forget, you got to practice those drawing skills. They're unavoidably valuable and therefore important. Okay, so here's just another example. I like this one just because of the horrors that come up if you do it the wrong way. So we have here a curve. Y'all will recognize from way back when that is a paraboloid. And in particular, it's a paraboloid that looks like this. And then we've got this one. And again, flashbacks to chapter 2, I guess it was. That's a paraboloid that looks like this. Our region that we're interested in is what's in between. And it's really hard to draw this. So now I'm going to highlight in yellow sort of what appears to be in between. But don't forget, there's actually some of our region, our yellow region, some of it comes all the way out to where this rim is. But if I kind of color it in there, it looks like I'm also filling in that little cavity in there. It's a hard thing to draw, right? Now you can slice this in various different ways. Do notice that some of those ways lead to really serious art challenges. No kidding, very difficult to the extent that I'm not very good at it myself. And let's, for example, let's do a DZ slice on the outside. What would that look like if I take a horizontal cross section of this weird solid? And it's, it's something along the lines of something kind of like that. Does that make sense? Which, by the way, would be easy to mess up as you're drawing it. If you mess up while you're drawing that, then you're going to be misled by your own picture and drawing wrong conclusions, and then it's just going to be catastrophe from there. So bad idea, and let's try not to put ourselves in a situation where we have to do something really hard like that. Okay, so this is a sales pitch for the projection method. So let's just notice it doesn't project very well into 2 of the 3 coordinate planes, but it projects really nicely into the XZ plane. The projection is pretty clearly a disk. Do a little algebra to find the particulars of that disk, right? But it's a disk. No, whatever, easy to deal with. And it has, for any given value there, right? If we look at any, let me suppose we look at a point like right there. For any given value, we look at the corresponding, what happens as I move in the y direction. Well, we start at points that are always on this surface. And we end at points that are always on this surface there. So we have the what I loosely call conditions met in the sense that, look, the projection is nice, and the lower bound surface is consistent and nice, and the upper bound surface is consistent and nice. So this seems like a great choice to me. It's not hard to draw particularly. I don't have to look at cross sections. I can do most of my work. Let's see here. Let me try to see more at the same time. Looking at the projection into the XZ plane. Therefore, putting my dx and my dz on the outside, right? I can look at that disk to conclude these bounds. Now, the details to be thought through, right? But that's a 2-dimensional slice up. We're looking at literally a disk in the XZ plane. Draw yourself a little disk in the XZ plane. It's two-dimensional analysis. And these are those bounds. And then the lower bound for Y comes from that surface, and the upper bound for Y comes from that other surface, as we've already established. So pretty easy to break down using projections, yeah.
I guess I'm a little bit confused by the shadow, given that like past y equals 4, it's a circle, like an outer circle with a hole in the middle. That's created if you slice it along.
When you say past z equals what? Say it again. I'm sorry.
So if we look like when y is greater than 4.
When y is beyond the intersection.
Yeah.
Oh well, then that's not the solid that we're interested in. So we're interested in the solid that's bounded by. So you're talking about a region of space that isn't bounded at all. Right? In other words, these two, you might say, let's look at kind of over here, these two surfaces are kind of converging together like this, right? If I had a mosquito in between, two pots, right? I'm in the kitchen, there's a mosquito, and somehow I manage to trap him in between two, like, pots, like so. He can't get out, right? So that's what we mean. That's one of the things we mean by bounded by. But if you look past that point, these two surfaces cross. Now the two surfaces are kind of diverging from each other, and it's unbounded. I mean, you see what I'm saying?
I guess I just mean to the right of where the red cylinder starts.
Yes.
Aren't you doing...
Not part of our solid. And that's one of the things that makes it geometrically confusing, right? Our solid ends here at the red surface, right? It's the region that is bounded by the blue and the red is only over here, and then once you get into here, you might say, one way I like to think about it, this is like a weird shaped little shot glass turned on its side, right? And the solid is where the glass of the shot glass is, right? You're talking about the region that's not glass. That's where you put your beverage. If you were ever to do such a thing. Right. Does that make sense? Anyway, the point is it's not part of our solid. So we don't have to account for it in the integral. Yes?
What about where it's still bounded, but like where your dot is, your red dot is, right above it?
Yep, in here?
Right there.
Yeah.
Wouldn't it technically not be a circle because you'd have the...
That was my question.
Yeah.
Oh,
there's a hole in the middle. Right there.
But you're talking about right here.
Yes,
No?
it's between the two lines.
Yeah, that is part of our solid.
But is it no longer a circle of the shadow?
Yeah, it would correspond to a point over here. Let me draw. So and I'll zoom in so we can see better. If I understand correctly, you're wondering where. Let me just clean up my picture, by the way. So what about a point here? Sorry, get into the better pen. So like, what about points up here? Is that right? Okay, so it's not going to correspond to those values of x and z. That's going to correspond to maybe something about like that. That value of x and z. And that would be part of what happens when, there's my lower bound for y, and then there's your upper bound for y, and we would 100% get to that point. Is that cool? Yeah. So the geometry on this one is challenging, and by the way, of course, I'm very happy to anyone who wants to hang out after class. By which I mean come to my office hours. We have to hang out downstairs instead of here because I have other students coming to that location. But we can absolutely talk about this to your heart's content. So come on into office hours. Okay. Let's move along to 5.5. This is an enormous section. Again, I like Collie's book very much. But she's made some aggressive choices with section lengths, right? We've already seen what was it, 5.3 was teeny tiny, right? And now 5.5 is going to take us easily a week, easily 3 lectures to get through, and frankly, probably more than that. Okay, so I'm going to start with a flashback. Y'all noticed, I'm sure, that I like to take single variable calculus ideas look at them a particular way, a very specific way, possibly not even your favorite way, doesn't matter, it's not the point. If you look at certain single variable calculus ideas from a certain point of view, it sets up a natural and convenient extension to sort of translate those ideas to multivariable. And that's what we're going to do here. So we're going to talk about the substitution rule. And y'all know that when you do a substitution, you've got a substitution function, and you'll, for example, have like here we have x being g of t, right? And when you do a substitution, this formula for x as a function of t is the basis for how you do your substitution. Okay. So, y'all okay over there? Okay. Right, so I just want to draw this so we can think of the t-axis being over here, and we can think of the x-axis as being over here, and any values of t that you have over here, you plug in, and out comes a value of x over to here, right? Does that make sense to everybody? Okay, and so likewise, we can talk about an entire interval. If I were to take this entire interval here from A to B, and if I were to say, look, let's just take all of these points, one at a time, all of these points, plug them in, and what comes out will be, in fact, another entire interval. And A goes to G of A, and B goes to G of B, so that interval from A to B goes to this interval from G of A to G of B. Okay. All right, now let's write down the substitution rule, and this is hopefully very familiar. Y'all will recall the substitution rule just says that this integral is equal to this integral. I hope that looks familiar. Yeah, right? Everybody's seen this before. Now, this might be a different version. Very often, the substitution rule is written about antiderivatives, not integrals. Again, important distinction. Antiderivatives are functions. Integrals are Riemann sums that evaluate and become numbers. And so they're different kinds of critters. So this is the integral version of the substitution rule. And you got to remember to plug in the bounds. And so, for example, when t is a, that would mean that x is, well, according to this anyway, g of a, etc. Does that all look cool? Is that satisfying? Okay, so I want to give you a take on this, a point of view, a way to think about this. I think this is really cool. First of all, I want to talk about the phenomenon of the pullback. I claim that we can think of this function that pushes points that way, right? G takes points on the left and produces points on the right. But the integral, I want to encourage you to think of it as we start with the integral on the right, and that integral goes backwards through the function. The term is pullback, is a slight abuse of the term, but I think it's natural here. I like to think of the integral as being pulled backwards by the function that's pushing forwards. Now, let me give you an example that I claim y'all have seen stuff like this before. I claim this is not creepy. And let's look at, let's see here. Let's have x be t squared. So this is my g of t. And now I'm not going to write down an integral, but if I have the t-axis there, then g pushes points forward, give you points on the x-axis there, right? Cool. This is how functions work. And now let's think about the following expression. If I think about the expression e to the x, that's a function of x. That's a function that I'm going to say it lives over here on the right side. What happens if I plug in? And by the way, this is not a creepy idea, right? Y'all have been plugging in. Hey, I have a formula for x. I can stick that where x goes. Right? It's just plugging in. You've been doing it forever. When you plug in, plugging in x equals t squared turns e to the x into e to the t squared. This is literally a pullback. Right? So the weird thing about it is functions will take points and push them forward, but functions take expressions and pulls them backwards. Does everybody see what I'm talking about? You probably never thought of it this way before, but I don't think anybody's creeped out by the idea of plugging in x equals t squared and e to the x turns into e to the t squared. And let's just observe, oh my gosh, it's literally going the other way. Okay, points push forward, expressions pull back. I claim that's what's happening here, right? We're going to think of having a g function as oriented here as taking an x integral, which we would then think of as being pulled back to produce a t integral. Okay. All right. So that's the first aspect of things. The second aspect of by the way, the actual plugging in, of course, is pretty straightforward. I'm literally just going to take x and plug in everywhere I see an x. I'm going to put g of t. That's not tricky. Okay, here's the other thing I want to recognize: the idea of a stretching factor. So we've written down, y'all have written down formulas like this many times, no big deal. We think of this as an algebraic thing, and that's fine. It has its, certainly you want to be able to think algebraically, and that's a nice example, I'm all for it. But I want to think geometrically. All right. So what's the geometric take on this expression? And I would propose it's like this: if I have a little piece of the t-axis of a certain size, let's call the size dt, right? That is going to have as its image a little piece of the x-axis. I'm going to say its size is dx. And we already know, again, flashbacks to chapter 2, we know what derivatives do. They turn input differentials into output differentials. It's the factor that you multiply by an input differential to get an output differential. And so the derivative, we know, goes here. It's what you multiply by dt to get dx. And geometrically now, how will we think of it? I mean, what's the, forget about the algebra, what does this look like? Well, it's like this little bitty interval here, this dt interval on the t-axis. I mean, G sends it forward, but it's going to make it a different size. The way I have it drawn here, it's bigger. It's like that little dt interval got stretched to become this larger dx interval. Is everybody buying it? Okay. And so by what factor did it get bigger? Well, it got bigger by a factor which is g prime. So I'm going to call g prime the stretching factor. And this is a very convenient little geometric intuition that we're going to use when we get to the multivariable version of this. And you can see it right here in the algebra. dx literally turns into dt times that stretching factor. And from a, I guess you might say an algebraic point of view, you can think of it as we have to insert the stretching factor to account for the fact that dx and dt are not the same. Yes?
Could we kind of think, or does this kind of follow the logic of like U substitution?
Yeah. Oh, yeah, U substitution is literally just, let U be what x is, then it's literally a U substitution. Yeah.
So would U subs be a pullback or a stretching factor or just mixing them?
The process of doing a, what you call a U substitution. And by the way, real quick moment, let's recognize there's nothing magic about the letter U of the alphabet, right? So let's just say substitution, right? This is literally and exactly a substitution, and it's both. A substitution, part of what you're doing with a substitution, I think should be thought of as a pullback, right? That's one aspect of what we're doing, and part of that pullback is this aspect of the stretching factor. Is that cool? Okay. Okay. All right. All right, so let's do the same thing in 2 dimensions. Now we're going to think about this in a different way. We're not going to think about this as, oh, I have an integral and we want to figure out how to rewrite the integrand because the integrand stinks. We're going to have a totally different set of motivations. But forget about the motivations for the moment. Let's just set it up like we had. So if we have some domain on the left, and if we apply some function, I can take all those points on the left, look at what their outputs are. That's going to produce some new domain on the right. Is that cool? Everybody happy? I don't know what this output's going to look like. I mean, this G function might be all kinds of weird. Who knows, right? So in recognition of this, I drew the original domain as a rectangle because it's nice and pretty. But even a nice and pretty domain, the image is going to be all kinds of weird. I don't know. I drew something deliberately weird. Okay. So yeah, let's now think about how we could continue. Well, the idea is that if I have an integral here, bad color choice. I'm going to use, okay. Anyway, if I have an integral here defined on that weird domain, I can ask, how would that pull back? Right? What would be the corresponding integral over here in the original domain? Yes?
How do you know that every integral has one?
Every what now?
Like, how would you know that it has a pullback?
Great question. You have to check that for sure. And what is the pullback domain? Well, you got to figure that out. And what is the G function that we should be using? That's going to be a matter of making good choices. Yeah, there's a lot to be worried about in that direction. Absolutely. So what I'm doing here is I'm setting it up. I'm basically assuming that. I'm saying I'm starting with this domain. I'm then starting with a function to apply to that domain. That will produce some set. I know that set has a pullback because I rigged it up that way. Is that yeah?
So you would have to know.
Yeah. That's right. If you just show up and have nothing more than this domain here, you got a problem. I don't know what G should I use, and I don't know what pullback domain I would have. Yeah. Okay. And we'll talk about how to make good choices on that. Yeah. Okay. All right. Yes.
What does that stand for? Is that some function?
I haven't gotten. No, it's going to be stretching factor. I just yeah. Okay, so the idea of a pullback is the same. I mean, look, if I have a function going this way, that literally is telling me that x and y are functions of u and v. Cool. Plug that in. That would literally just be the plugging in process. Everywhere you see an x, you put in whatever the formula is for x in terms of u and v. Likewise, y. And then there's also the idea of the stretching factor. And we don't know how to compute this yet. But this piece of area here and this piece of area here, not the same size. Necessarily, right? Why would they be? We wouldn't expect them to be. G could be doing all kinds of crazy stuff. And so we're going to have to figure out if I want to be able to replace dA with something that I write in terms of u and v, I need to know, okay, well look, dA is not the same as du dv. I need to know what is this factor by which I need to multiply the blue area to get the green area. And that's going to be a problem. That's something we're going to have to figure out. But this is the big picture of our strategy. Everybody kind of see what we're trying to do here? Details to be determined? Okay. For the moment, I'm just going to tell you the formula for the stretching factor. And we'll justify it, or at least I'll wave some hands and say a few words about where it comes from in a bit. But we got a lot going on right now. I don't want to get distracted in the weeds. So for the moment, I'm just going to assert. Here's the formula for the stretching factor. It's the absolute value of the determinant of the derivative matrix. It's a nice, compact little formula there. Very convenient. So that's nice. Now, reminder, the derivative matrix is that right there. Right? Flashbacks of chapter 2 again. Right? Same derivative matrix from chapter 2. Reminder, sometimes this derivative matrix, sometimes called the Jacobian matrix. And related note, the determinant of the Jacobian matrix gets used a lot. This is one of the big reasons why. And so the just to streamline the language, very often people will call this the Jacobian determinant. Right? So you're going to hear the term Jacobian determinant. And by the way, some people will just refer to that determinant itself as the Jacobian. It bugs me because to me the Jacobian means a matrix, not the determinant of the matrix. I think that's confusing, but anyway, common terminology. Okay, one last little bit of notation. Not the matrix, not the absolute value of the determinant of the matrix, but just the determinant of the matrix itself. That determinant is sometimes written as this little fraction-looking thing, which very importantly, not a fraction, right? Look at it. Here's the formula. This thing, it's a determinant. Determinant's not a fraction. It's a formula. Right? So we write it as a fraction even though it isn't actually a fraction. And we write it that way because it ends up behaving like a fraction in some very convenient and intuitively satisfying ways. So anyway, heads up for this notation as well. By the way, big fan. I like this notation. I use this notation regularly. I think it's very convenient. And yeah, it's a little suspicious, a little fishy because it's presenting as a fraction, something that's not a fraction, right? But man, it sure does behave like a fraction, and it sure is convenient. And I'll show you how in a couple ways. Real quick, the first observation on that is, if you think about it, if I were to take this du dv here, and if I were to multiply by this stretching factor, partial xy, and let's use this questionable notation, partial xy, partial uv, and if I were to claim that produces for me little bits of area in the xy plane, which we're accustomed to writing as dx dy, notice that it's as if, oh gosh, and I get the willies just thinking about doing this, but it's as if that cancels with that. You know? Now they don't. This isn't a fraction. That denominator is not a thing. This is nonsense, but isn't it satisfying that it's like the UV's canceled and you're left with the XY's, which is what we're supposed to have? It actually kind of sort of works. And the good news about it, it works every time. This is consistently convenient. This will consistently keep it straight for you. This is one of the big reasons that I like this notation. Okay. All right. So let's do one. Let's get our hands dirty. Note the setup. I am assuming that we start with a rectangle, unit square in the UV plane. I am assuming that we are given a change variables function g. X and y are functions of u and v. Right? And notice that produces, if I then look at, what's the image, what comes out when you take those blue points and plug into that purple function, what's going to come out is some weirdo set, something maybe kind of, I think it's about like that. And now, let's suppose that we're interested in doing an integral that's defined on this domain. So, for example, maybe I want to compute how many people live in this oddly shaped county, or maybe I want to know what's the volume of water in a lake for which this is the footprint, and I know how the depth varies with the position, or whatever, right? I want to compute some integral in this domain. Everybody see the setup? Well, We know how to compute integrals. You want to compute an integral, you start slicing, and now what you notice very quickly is that whichever way you slice, you're going to hit that corner and that corner. You're going to have 3 iterated integrals, whichever way you slice. Right? Everybody see that? It's worse than that. Because you're going to have to find on these curves, if you're doing dx dy or dy dx, you're going to need to understand the relationships between x and y. I don't have a relationships between x and y. I have different formulas for x and y in terms of other things. So I would have to figure out, I'd have to sit around and play around and figure out how these formulas would allow me to write either y in terms of x or x in terms of y. And that's work to be done. It's doable, but it's work to be done. So, pretty undesirable way to solve the problem. Is everybody with me so far on how we're going to call that, hopefully we don't have to do that? Yeah? Okay, so we're going to do a pullback instead. And I'm going to say, let's see, you're coming back up here. If I want to do the pullback, apparently all I've got to do is figure out what this stretching factor is, plug in whatever formula I was given for x and y, and we're done. So let's find the stretching factor. Now, a little bit of algebra, no big deal. Here is our function. Here's the derivative matrix of that function. Make sure you can do that. Flashbacks to chapter 2, right? It's very important to be able to do those computations. You got to make sure to arrange the partials the correct way. In this case, it's symmetric, so that's convenient, but it won't always be. Then we got to take the determinant of that derivative matrix. Fine, no big deal. And then checking back to our formula, notice that our stretching factor is, very importantly, an absolute value of that Jacobian determinant. And that's an important part of the formula. Got to have the absolute values in there, not optional. Okay. So now I have a nasty little problem. And sometimes this is an inconvenient thing. But I've got to figure out how am I going to compute the absolute value of this expression that is our Jacobian determinant. So I need the absolute value of 4uv minus 9. How are we doing? Is everybody on board still? Everybody still following? Okay. Okay, so how do we do this? I claim that this is actually pretty straightforward in this case. Everything we need is on this page looking at us. Yes?
I don't get how you got the absolute value.
That's
why is there a minus sign in the absolute value?
I'm about to explain why it's a minus sign, but the absolute value is the formula. Is that cool? Yeah. Okay, so how do I know how to evaluate this absolute value? Well, check it out. This u right here, the premise of the question is that my pullback domain is this square, and on this square, u is always between 0 and 1. Right there in my picture. Is that cool? Likewise, the premise is that v always between 0 and 1 also, again, because there it is. That you can see the shape of the domain, and v is, in fact, always between 0 and 1. So that gives us everything that we need. U and v individually are always between 0 and 1. That means the first term, 4uv, is always between 0 and 4. And that means that when I subtract 9, I will always, every time, no exceptions, I will always get a negative number. Everybody with? Does that make sense? And now, we've got to infer that from the picture. I'm going to say the picture, at least what we know about the pullback domain. That tells us how to interpret U and V. You can't just make up whatever you want there. So, but in this case, the picture is the dead giveaway. And recall flashbacks to high school algebra. The absolute value of something that's negative is the negative of that thing. Is that satisfying? Everybody remember that one? Yes.
If the square, like, on our domain is bigger, so it went from, like, u equals 3 to...
Yeah, then we'd have a problem.
But we have to do, like, 2 different integrals.
Yes, that's right. So what you'd have to do if this was a oh gosh, let's see here. If this was a different formula that was, let's say, negative for these values and positive for those values, then sadly you'd have to break it up into two separate integrals. And on the sort of the lower chunk, you treat the Jacobian determinant as negative, which it is. And on the upper chunk, you treat it as positive, which it is. And then, you just have to do two separate integrals. Yeah. And I'm not going to say that I'm not going to do that, but I am going to say that I'm not inspired by that kind of question currently. Let me say that. Does that satisfy? Yes.
Yeah, then like another question. In this single variable, like application of this.
Yeah, where's the absolute value?
Yeah.
Yeah, that absolutely. That's a great question. It is hidden. So let's look at this case. We have A to B, and so B is greater than A. Right, we're in some sense going that way. Let's think about what would happen if this G prime were negative. Let's just say, if that G prime were negative, then the function's kind of going this way, which means that G of A would be the bigger value, G of B would be the lesser value. We'd be going sort of the opposite way, and the fact that this is the larger number, this is the greater number, and this is the lesser number would imply a minus sign correspondingly on the right. So ultimately, it's kind of a notation thing. The way we write integrals in single variable, it's what we call an oriented domain. When I write it down, I'm implying, look, whichever one I put here, I don't care if it's greater, I don't care if it's lesser, but this is the one that I think of as where we start. Right? And this is the one that I think of as where we end, and that will imply going backwards sometimes. And we just don't write it that way here because I don't even know what that would mean. Right? And so that's the reason for the difference. Great question. Okay, so back to it. We have our stretching factor, and it's kind of all over with the shouting at this point. Remember that let me get into the highlighter mode. The dA that was on the right is stretching factor times du dv on the left, and we just computed our stretching factor like so. So don't forget to plug in your stretching factor. It's an easy thing to forget while you've got other things going on, but make sure to plug that in there. Really big deal, of course. And for the rest of the integrand, it's literally just plugging in. X, for example, that X says right here that X is u squared plus 3v. Straight up, literally, plug it in. Does everybody see what I did there? There's a takeaway, by the way, from this. Very often students forget, hey, wait, what do I do with the X? What do I do with the Y? How do I... don't forget, the change of variables function itself is the instructions for what to do as you plug in. So make sure you have a unambiguous and clear and crisp understanding of what your change of variables function is. That tells you how to do the plugging in portion of the process. Yeah.
So for the bounds, how do you know what the bounds?
Oh, yeah, absolutely. So that's kind of the cool part. That's sort of automatic. So our setup was that we started by presuming that we have a domain here, and we were going to look by way of the change of variables function at literally its image, right? And then just like in the substitution rule, the integral done over the output domain turns into an integral that's over the input domain. Okay. That's why we set it up that way. And so the domain becomes whatever the thing is whose image is that domain, that, what I like to call a pullback domain, is the domain for your new integral. Yeah.
The Jacobian that wouldn't be in the.
Do what now?
Would the Jacobian be in the domain because it is the factor that you're stretching by, and you have g times.
So the stretching factor is an algebraic expression. So yeah, it goes in the algebra, absolutely. I wouldn't say it's in the domain because the domain's a set, right? Does that make sense?
Yeah.
Yeah. Yes.
Is there any chance you could just show us an example of how you would solve the bounds for the problem we were just doing?
Oh, yeah. I'm not done yet.
Okay, I'm so sorry.
Yeah. No worries. Yes.
So if we were given like the unit square value,
Yeah. How do you find the pullback domain? We're going to talk about it.
Okay.
Yeah, and the answer is, if I were to take a random domain and a random change of variables function and ask you to then produce, oh my God, that would be hard. We're not going to really do that, right? What we're going to do is we're going to look at a few carefully constructed, we're going to rig it up basically so that the pullback domain will be something that we kind of, we rigged it up to be convenient. Yeah, that's kind of the short answer all the time, yeah. Okay, so let's finish this example. So we have our, let's see here. We started off with an integral on this domain. I've done the pullback, at least the algebra part of the pullback. And I'm claiming now that my new integral is an integral on the pullback domain. And so that is literally and exactly what this new domain is right here. I forgot who asked me this. Yeah, okay, yeah. So this new integral, after I've plugged in for the x and y, don't forget your stretching factor, don't forget the absolute values as you compute, blah, 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 algebra. But what is the new domain? It's the pullback that we set up in the first place. And so if you were to, when you write this UV integral out, this, u and v, I mean, look at your domain over here, u and v are going to go from 0 to 1 and 0 to 1. Okay, now this was a highly manufactured example. Let's take a moment to recognize how artificial this is. I just presumed, right, as part of the statement of the question, I started with the pullback domain. This is not life. In reality, how it's going to go down is you're not going to have that given. And you're not going to have the domain in the XY plane given. None of that. Forget that. You're just going to have, hey, I want to compute this integral on that domain. Go. And you're going to have to figure out, oh my God, what is my... can I think of a good way to... Yeah, and you're going to have to kind of figure for yourself how to arrange it to where you have a domain and a change of variables function that will make this an image so that you can then talk pullbacks. And here are some examples that tend to be useful. This is not intended to be a complete list. This is just a couple examples that are useful sometimes. Translations, stretches or squishes, whichever. Rotations. I'm going to do an actual example of this on the next page. And just keep in mind that when you use certain change of variables function, then this is what's going to happen to the pullback, and there's a kind of an oppositeness. If your change of variables is counterclockwise, that's effectively going to rotate clockwise as you do the pullback because you're going backwards. Likewise, and we're going to see that explicitly, if your G translates by the vector AB, in the pullback, your domain will effectively be translated backwards. And here's why. Let's see an actual picture here. If I start with a domain like this, and if I translate like so, notice I'm adding a comma b to everything, right? That entire green square is going to get translated by the vector a comma b. It'll then find itself something like that. Oh, that's too big. This green square will get translated to be something like this. If you take the point of view of, hey, I want to compute an integral on this domain, what's the pullback domain? Well, the pullback domain goes the other way. So something to keep in mind. And we'll see that in action in this next example. Okay, so this is a very realistic, real world kind of example. I've been asked to compute an integral on a domain. The domain is this square with given vertices. So my domain is this shape right here. How am I going to compute an integral on this shape? Oh my God, with the corners, so many corners. This is going to be 3 integrals. dx, dy, dy, dx, take your pick. 3 integrals. Okay. All right, so I'm going to think to myself, can I view this undesirable domain as being an image of something? Is this the result of doing something simple to something simple? And it is. This is the result of doing a counterclockwise rotation of this square, which just for sort of geometric convenience, I'm going to sort of draw over there just so you can see which direction the rotation goes. That green square that we need is a counterclockwise rotation of this totally awesome domain right here, right? Everybody's favorite domain for a double integral should be a rectangle, right? A constant bound, super easy to write down, nothing to it. Okay, now does everybody see how I did that? Right? I had to use a little bit of geometric intuition there. I'm looking at this green square and I'm thinking, what simple function applied to what more desirable domain gives me that green square? And you just kind of notice, well, check it out. It's just a rotation. Effectively, it's like I want to take my green square and rotate it clockwise. And I do that by pulling back, by recognizing that it is produced by a counterclockwise rotation. And so now we just have to do a couple of details. This change of variables function, the counterclockwise, by the way, notice that my angle here, the angle of that rotation, you can do a little bit of arithmetic, that's pi over 6. Little trig, make sure you're good with that. And we know how to do rotations, right? So here's how you do a rotation. Old news, linear algebra. And we talked about that a long time ago. Make sure you can do this, right? Flashbacks to chapter 1 and before that linear algebra class. So there you have it. There's your change of variables function. X and Y are functions of u and v, like so. And then you just compute your stretching factor, plug in, bada bing, bada boom, we're done. Let's see. I don't need to leave that in there. Easy to lose track, of course. Actually, here, let me just finish it up real quick, and then we'll pause for questions. This X right here. How do I rewrite X? Don't forget, X is one of the outputs of my change of variables function. And so X is literally that dot product, which is that. What do you think? Everybody see what happened there? Don't forget the stretching factor. The stretching factor for the rotation turns out to be 1. That's nice, but nevertheless, just keep in mind, it's not about the answer. It's about showing you understand the process. In recognition of that, please do actually, insert into your algebra, even though it's a 1, even though it doesn't affect the answer. Go ahead and stick it in there. That's how I know that you knew that that's where it goes. right? Does that make sense? And then new integral. What do you think? By the way, is this a win? Or was this a bunch of waste of time? A lot of people would say, look, I started off with an easier looking integral and now I've turned it into a harder looking integral. How is this good news? Well, first of all, is it really harder? The constants are weirder constants, but it's still just, linear, u's and v's instead of x's and y's. It's not really a harder integrand. The point is that we've taken a highly undesirable domain here that's got corner problems and that is going to turn into 3 iterated integrals, and we have turned that into a new domain that is, again, everyone's favorite domain, rectangles, aligned with the axes, constant bounds. Gotta love it. This is a big win. Right, this cut our workload by a factor of 3. Very, very nice. In fact, more than 3 because these bounds are constants and these bounds are not constants. So probably 4 or 5 times harder to do it that way. Okay, y'all have a good weekend. See you later. We'll pick up here next time. Okay.
Thank you.